very happy to have today Jeff Xu. Jeff joined us just a few months ago at this point, a couple of months ago from CMU, and I'm very interested to actually hear about Tensor PCA, which is something close also to my heart. And Jeff is joined us as research assistant professor, and will be here for 3 years, so we should all get to know him. Thank you.
Thanks for the introduction. Hi everyone, I'm Jeff. So I'm going to talk about a recent work with my PhD advisor, Pravesh Katari, now at Princeton. And I hope this work gives you a taste of what I like and what I work on. So let's get started. Quick words about myself. Yeah, as Mehdi said, I'm a new IAP, just joined actually a month ago maybe. And I work mostly on statistical inference and information computation gap. And previously, during my PhD, I have been primarily interested in hardness or lower bounds for average case problems, especially against the sum of squares SDP hierarchy, if you know about it. And lately, I have been more interested in exploring connections and applications beyond average case hardness. And please feel free to interrupt me throughout the talk. I will try to speak slowly. Yeah. So, okay. If you get absolutely nothing out of my talk, at least you know about me and what I like. So feel free, and please talk to me. Like, I don't have too many things here. But let's get into business. And today's talk is about smooth trade-off for Tensor PCA. And let me tell you about the problem setup. What's a tensor? In this talk, we are going to consider an order R tensor. It's just an array of dimension n by n, and there are many of them. And for this talk, we are going to focus on symmetric tensors. And here's a picture for a third order tensor given by ChatGPT. Okay. I hope everybody has seen tensor before, but don't worry if not. And here we are going to consider the PCA question on tensor. Or you can also think of it as like degree R polynomial maximization. This is a model put forward by Montanari and Richard in 2014. Here, we are going to consider input, which is an order R tensor T, given by the following form. We are going to sample a signal V, say from plus minus 1 to the n. It's an n-dimensional Boolean vector. And then consider the rank-1 tensor of V to the R. We are going to consider lambda as the signal-to-noise ratio, which basically measures how strong our signal is. And then we are going to consider that this signal is perturbed by some noise, which you can think of it as Gaussian or Rademacher tensor for now. So for each set S of size R in this order R tensor, the tensor entry corresponds to this set TS is just going to be given by lambda times product of all indices I in S, Vi, plus the corresponding Gaussian noise for this entry.
This is probably, I'm a bit confused why is S. Should I really think of S as a set or as a sequence?
It's a sequence. It's a subset.
It's a multiset, you mean to say, yeah.
It's a multiset, but
Multiset.
for now let's focus on
Multiset.
It's a multiset.
Okay, so
Partition.
fine. Sequence, yeah, fine. Okay,
So,
okay.
yeah. Maybe I should think of it as choose n to the R.
Yeah.
Gotcha. And the question we are going to focus on is when can we detect or recover the signal given this tensor? You can also equivalently think of it as given a tensor T that either has this rank 1 component or not, when can we tell whether it is there or not? And this is a recurrent thing in many statistical inference problems. To give you a taste of this area. And here's an obvious algorithm I want to say. For intuition, let's look at order 4 tensor. This question should be easy if my signal-to-noise ratio lambda is at least some large constant times log n. Log to some constant power of n. Do you see why? Like if lambda is at least this, given an order R tensor T, I can easily tell whether it has this rank 1 component or it's just purely Gaussian noise from N01.
Gaussian means standard Gaussian.
Yeah.
Variance as well.
N01, yes.
Just the numbers.
I think we can just look at
Conjecture.
Just look at the magnitude.
Yeah, just look at magnitude of the largest magnitude. You have very nice concentration for Gaussian ID Gaussian random variable. It's at most order log n, root log n. Okay. But yeah, if lambda is big, the v to the I is like of order this lambda of this magnitude. So you can easily tell.
So instead of 1,000, why do you do log to the? Why do you have to do log to the 10?
No, I'm just being safe. Arbitrary constant.
I mean, one would.
One
Just 1,000 log n would not be fine.
1,000 log n should be fine. Yeah.
Okay.
If R is 4, unless R is gigantic.
Okay.
Yeah.
Great.
For this thought, the constants are very arbitrary. Like, just
If you pick a random coefficient, then it will be close to plus minus 1 with high probability.
yeah.
And if you take sufficiently many of them, then I believe you can recover one.
So what's the question?
You asked us.
Yeah. Sorry.
I'm trying to answer it.
yeah.
It's not the question.
I just meant it is.
Sorry, for arbitrary R, what would be the lambda?
I think you may have log to the R to over 2 because you're taking union bound over the obvious algorithm. But let's not worry about
Union bound over what?
Hmm?
Union bound over n to the.
it. Into the R many entries of the tensor.
Sorry.
Yes. But it's the obvious algorithm. We're going to look into something more fancy in a bit. So yeah, when lambda is big enough, I'm just saying, like, you can clearly solve this question. But is this the best we can do? Not quite, maybe. So here's what we know about this problem. We know that when lambda scales as n to the 1 minus r over 2, so in fact, it's an inverse polynomial. Once lambda is at least this threshold, this question can be solved. Like, we have enough information if we don't care about runtime. However, if we have some concern about the runtime, we are going to parameterize the runtime by n to the L, let's say. So we are going to look at the polynomial time regime of L equals to order 1. Here, due to a work by Hopkins, Xu, and Stoyer in 2015, we know that this question can be efficiently solved if lambda is at least n to the minus r over 4.
Is it they work based on sum of squares?
Yes, it's based on sum of squares. And I think there are some like speed up you can do after. So this is actually much better than the log n algorithm or the constant or the threshold we just saw.
So is that threshold for information theoretically, is that tight or
This
is
is
that just a log? Okay.
And we are going to see the algorithm actually. And in fact, we know that in exponential time, we can nicely interpolate between the polynomial time threshold of n to the minus r over 4 and the information threshold of n to the 1 minus r over 2 due to a sequence of works in 2016 through 19. And they are mostly based on sum of squares hierarchy and some special algorithm. And in fact, here is one example where we have a phenomena of information versus computation gap. Right? We know that above this threshold, we have enough information to solve this question, but we conjecture that there is no efficient algorithm to do so.
And sorry, so how should I interpret that O of 1 there? L equals O of 1. Should I just, is R, when you write there, that dashed line is for n to the constant?
Into the constant.
But how should I interpret that constant? Does that depend on R or is that for, should I fix?
Let's fix R to be constant.
Okay.
Some large constant. Yeah, it can be large constant. Some constant.
Okay, so it's for every R, there's an L.
Yes, for any R data. Yes. Yeah, in fact, you can take L to be R over 2.
Okay.
So let me tell you about the algorithm for detection that at least that matches this threshold for any L, actually, not just L equals order 1. Here, we are going to consider this algorithm put forward by Kikuchi hierarchy. Here, we are going to think of it, look at the level L Kikuchi matrix as the following object. This is a random matrix. This is a matrix you can build once I give you a tensor T. And this is a matrix, a gigantic matrix, I should say, of dimension n choose L by n choose L. So it has rows and columns indexed by all subsets of size L. It can be multi-sets, but for now, let's just look at it as subsets. The minor difference doesn't matter too much here.
So I have Matthew's question again. Are these sets or multi-sets?
Let's look at it as sets now.
So you are looking only at those coefficients that are don't repeat indices.
Yeah, there's no. So we have rows and columns indexed by all subsets of size L. And for the corresponding entry for set I and j, we have a non-zero entry coming from Ti delta j if I delta j is some and correspond to some entry in the tensor. Which means that they have symmetry difference exactly R. And otherwise, we just put 0 in this matrix.
Sorry, what's the rank of your tensor?
The rank. So this is a matrix you can build for any tensor. But the tensor is, if you have a random tensor, it's going to be full rank with high probability. But this is a matrix you can build for rank 1 tensors.
Rank you probably mean dimension.
Okay.
Or
And here's an example. If you look at a first order tensor T and L equal to 6, so if you have set I equal to A, B, C, D, E, F, and J is I, J, C, D, E, F, we just put entry corresponding to T, A, B, I, J in the tensor for the matrix entry, for the matrix Mij, matrix entry of Mij. So I just want to say, like, when T is a random tensor, this is a random matrix also. And this, yes.
By the third claim also, which says in first non-zero.
Because it's by definition. Like if I intersect I delta j is not R, exactly, I'm just going to put 0. Because there's no corresponding entry I can find in the tensor.
Okay.
Right. There's a type mismatch. So I claim that this matrix is going to give us a distinguishing algorithm if we just look at the special norm of this matrix. Where we recall that special norm or operator norm of the matrix is just the largest magnitude eigenvalue within the symmetric matrix. So in this case, we want to show that for a spike tensor T, if we have this rank 1 Boolean component put in, the special norm of this Kikuchi matrix, this gigantic matrix in dimension n to the L by n to the L, is going to have much larger special norm than if you just put in a random tensor, a random Gaussian tensor, or rather marker tensor. So to show this is like fairly standard spatial algorithm. We are going to say that, okay, in the one case, if you have the Boolean component, this matrix has large eigenvalue. How to see that? We are going to consider a test vector V in V tilde, let's say, in dimension n to the L. So it's indexed by a subset of size L again, where for each entry V tilde S, we are going to put the product of I in S, Vi. This is a vector you can build if you know the signal. And then now we are going to just lower bound the special norm of this Kikuchi matrix by evaluating the quadratic form on this test vector. This is at least V tilde. And then I'm going to further write this gigantic matrix as having two components. There's one component depending on the rank 1 V, and one component just coming from the Gaussian nodes G. I'm going to lower bound the quadratic form loosely by just lower bound the quadratic form on the rank 1 component, and then upper bound the contribution coming from the second term by the special norm of the Gaussian, the Kikuchi special norm on Gaussian tensor. So our focus is how big is the first quantity here? And let's just expand it out. If you evaluate the quadratic form, this is equivalent to summing over all indices ij, which is now a subset of size L, such that they have this symmetric difference. Otherwise, Mij is going to be 0. And then we're going to multiply by the corresponding v tilde I, v tilde j. And here's something we know from the construction of our matrix. When you have a rank 1 component, the entry of this matrix, Ij, is just going to be given by lambda times vi delta j, by definition. Nothing fancy. And then we also know by construction of our vector, the test vector v tilde, the corresponding entry is going to be the product of vi times vj. And we can also rewrite it as the symmetric difference times whatever indices in the intersection squared. Just because every vertex, every indices in the intersection, they appear twice in both of them, in both vectors. And then for the symmetric difference ones, you appear only once. Good. And because the vector we're planting here are Boolean, we know that the square of each entry is just 1 after we combine them. That means that this equation is barely just lambda times summing over all indices I in choose L, and the degree of I, which is also just, you can think of it as lambda times the number of edges in this matrix. A number of non-zero edges in this matrix. And what's the degree if I fix a vertex set I, let's say? Recall that this is only non-zero if we have another vertex set J that gives you a symmetric difference of order R, like symmetric difference of cardinality R. And this can be chosen, like once I tell you I, you can determine J by first picking the vertices that you are going to kick out from I. And you have L choose R over too many choices. Let's say R is even for now. And then you are going to swap in R over two new vertices. After you keep the other R over 2 out, and you have roughly n to the R over too many choices for the new ones. So the degree is really just the product of these two terms. And we're going to call this number D. And in fact, you can also observe that the Kikuchi graph is very regular, like it's actually a regular graph of degree D. Now, let's proceed. Why were we lower bounding this? We are trying to say if you have a rank 1 component, the special norm is large. Let's complete this calculation. We have just seen that, okay, the numerator is going to be lambda times n choose L times D, and then the L2 norm of the test vector, it has plus minus 1 entry at each non-zero entry, and then it's indexed by a subset of size L, so it's like L2 norm into the L, n choose L. So like the n choose L vector cancel out nicely. This is just lambda D minus the special norm of Mg, where Mg is the Kikuchi matrix you can build out of a random symmetric tensor. And this is going to be the focus.
Can you remind the definition of Mg again?
Mg is this matrix you can build coming from T when lambda is 0. Let's say if you look at Mg, you have just a tensor of order G, and then you build this matrix. So you can also think of it as like in this entry, it's just going to be precisely G I delta J.
It's a random variable. Random.
It's random. Let's say it's IID random.
No, I'm saying the MG is a random matrix, right?
Yeah, it's a random matrix, but it has correlations across.
Sure.
So at this point, like, what would you say is the motivation of considering this conjecture matrix?
What's the motivation? There is only one matrix or one algorithm to give you the tight threshold. But I think it's just easier to analyze. Like there are other matrices you can consider.
So just to check that I understand it right, it will be actually the sum of independent Gaussian matrices where every matrix corresponds to a single value of.
Yes, we can write it that quickly. But it has correlations because you have different different entries depending on the same random variable.
Yeah, but it will be
You
a
can write it
matrix
as
that's.
Yes.
So, or in other words, I mean, it is a Gaussian symbol, just not IID. I mean, it's some covariance, like some very structured covariance.
Yes, very structured matrix. So, okay, going back, we want to say that the special norm, when we have a rank 1 tensor, it's much bigger than when you don't, but when lambda is 0. So, rearranging, this is equivalent to bounding lambda to set lambdas by 1 over d times the special norm of the random tensor's Kikuchi norm, Kikuchi matrix norm.
Oh, how does the actual distinguisher work? Just take the largest eigenvector and look at it, yeah?
Yeah, just look at the eigenvalue impact. Now, if it's much bigger than what you expect from a Gaussian tensor, just say, oh, something wrong is going on. And here's what we know from random matrix theory. If G is a random Gaussian, N01, each entry ID, and if you build a Kikuchi matrix out of it, it has special norm, square root D times square root L times some polylog N factor. So rearranging, this gives us a distinguisher when lambda is order root L over root D times some extra polylog factor. And then if we plug in the degree D, which is the product of n L to the R over 2 and N to the R over 2, rearranging, you can see that this is the threshold that you get from this algorithm that runs in time n to the order L. Question?
So we're just going to my question 4.
Yes.
So the runtime, it's not the runtime is into the R over, it's like, it's n of O of R, but this O of R is,
It's going to be killed by, it's going to overbe, think of L as much bigger than R.
right. No, but in terms of the runtime is not O of L here, it's O of,
It's like you build a matrix in, this is an n.
oh, it is exactly n,
Yeah.
n of L.
O to the n to the L.
No, O to the L, but not n to the O of L. I thought it's like going to be n to the 2L or something. Okay.
Yeah.
No,
Yes.
it is n to the L.
It's n to the L in this case. Yes. But yeah, we are going to see the constant.
Oh, and then you have to calculate the spectral norm, and that also you can do in kind of.
Like power method, just.
Yeah, okay. I believe you can do it.
So, in fact, this algorithm is known before our work. Like, we know that for any L between 1 and n, there is an algorithm that runs in time n to the order L. But as Nancy said, you can be precise in the constant. You're not going to be. That solves the detection and recovery question. The corresponding threshold lambda here. So this question has been solved. Right? This is a 2019, and in fact, previous was even earlier. But why do we want to open up this question again now that in 2025? Here are some motivations. And let me tell you about that. One motivation is coming from TCS, and it's really this central question of refutation of random CSP problem. For random CSP problem, you can stare at it and then kind of view it as a sparse analog of our problem. Because instead of putting IID Gaussian tensor, which is a dense matrix, you just put some sparse matrix instead. And this question has been investigated previously by Tommaso Dossi and Luca Trevisan in 2023, where they can show a bound that does not contain extra polylog factor. But it was interesting for us because their technique really relies on the underlying graph being sparse, because they need to use this Ihara bars or non-backtracking operator, if you know about that. So they don't really apply for these dense Gaussian matrices. That's one bottleneck. And another bottleneck that we really care about is that their result is really specific to L being R/2. So in that case, this is really just an IID matrix. But you don't have these extra vertices lying around. This is an n to the R/2 by n to the R/2 matrix. They're really just looking at the basic level.
Can you help us understand how CSP corresponds to this?
Yeah. So for CSP, you can think of it as it's like you get some sparse observation of this tensor.
When
Yeah.
you basic,
Yeah, like think of V as the underlying ±1 satisfying assignment.
okay.
And then now you only see like few clauses. You don't see all the clauses. Instead of seeing n to the r many clauses, you only see like some subsample clauses. So this corresponding to G being ±1 but sparse. Let's look at this in R equals to 4. Maybe look at 4 XOR, random 4 XOR.
Okay.
Yeah, for random XOR, the corresponding matrix you care about is going to be this matrix n squared by n squared, and then you only have ±1 sign if there is a clause on IJKL. And then for random CSP, you care about like the sparse regime. Instead of looking at n to the equals to n to the 4 many constraints, you are only looking at like n squared many constraints or even fewer in the interesting regime. So you can think of G as a sparse tensor instead.
Because you don't. I mean, G is the noise. Is the
G is a sign. You can think of G as a signing for random instance.
Oh, so G is like the source I would get for a random assignment.
Yes.
If I chose random ±1s.
Yes.
But
so G is a hypergraph.
okay, maybe
Yeah,
we'll,
we're gonna
I'll
apply.
try to figure out later.
Yeah,
But I
yeah.
don't. Yeah.
So,
But by CSP you mean specifically XORs, or this also works for other, like for SAT or other? CSP?
kind of works because for any set you can write it as TXOR. You can expand it out using Fourier.
With an exponential blow, but yeah, okay. Yeah.
Because for reputation, we in fact just care about the top level. That's the hardest one.
Okay.
Oh yeah, so the previous techniques coming from CSP reputation does not apply because we are in the dense case and the restriction on L. And also we have some motivation coming from extremal combinatorics. This is about hypergraph move-bound. This is what move-bound is about. For a graph, it asks for what is the largest number of edges in a graph of order n, and if the shortest cycle or the girth is at least G. And this is related to the question in the hypergraph, which asks for, instead of having shortest cycle, you look at the natural analog of cycle in hypergraph, which is even cover. And we still don't know the type bound for hypergraph at the moment. I can say more why this question are very closely related in a bit. And another motivation really comes from this recent work by Ryan and co-authors for quantum quartic speedups. They show that the L's level Kikuchi matrix, the precise one we have here, can be computed in quantum time n to the L over 4. but classic power iteration, because you need to write down a matrix of n to the L by n to the L. This actually takes time n to the L. So it gives you a 1/4 saving in the exponent. And this is interesting because usually we only expect a square root saving from like black box reduction.
I'm a bit confused about this result because this matrix, it has size roughly n to dl.
Yeah.
So you need n to dl bits quantum or not even to represent it.
Yeah, this is 2L. I should say it's 2L and L over 2 here.
Ah, LP over there, yeah?
It's over 2. Like, but it's like, okay, it's 2L and L over 2, but you are saving 1/4 in the exponent.
Ooh. But still, how can it be L over 2? How many bits do you need to represent the input? Usually bits or qubits, but if you need n bits to represent your input, then capital N, then it can be smaller than capital N unless something interesting happens.
Actually, I'm not really sure. We can check out.
Okay, good.
Yeah, I'm not familiar with that, but it's just the quartic saving.
Good. The line is sparse, probably. Whatever.
Okay, now I can say more about this motivation, and this is this is like dear to my heart, I would say. It's really this recent line of work that I try to give improved matrix concentration bounds from techniques in non-asymptotic free probability. There's a line of work by Bandera, Pudihajo, and Van Handel, and then some follow-up work by co-authors. So their work develops more general techniques for tightening non-commutative Kim-Chain inequalities in restricted settings. So if you apply like black box NCK inequality for matrix concentration for this matrix we have here, we are gonna expect a bound of square root D, which is what we usually expect of average degree. And you're gonna get this extra factor coming from log matrix dimension. And because we are looking at gigantic matrix of dimension n to the L by n to the L, this is L log n. And okay. So it's an extra factor of root L log n in the final non-bound. And in a recent work by Bandera and co-authors, they show that for random Gaussian tensor, I'm not sure if they work for Boltzmann as well, but definitely Gaussian, the bound can be improved. Like the extra square root log dimension can be entirely shaved off, provided your L is not too big. It's in this very restricted regime of R over 2 and 3/4 R. And they don't even work for L equal to R. And they ask, like, okay, what's happening? Like, they can and this is less satisfying because for Kikuchi matrix, we usually think of L as much bigger than R, so that we can get this nice interpolation. And yeah, this is really bizarre for them because they can observe that their technique using free probability just fails for larger L. Like what's happening? And yeah, this is our main motivation and also our main technical result. We look at the same matrix they have. But now we are going to remove the restriction coming from small l. We are looking for any l. We are okay with l growing with polynomial in n even. And then we show that the bound can be replaced by square root d multiplied by square root l with the same d. So as one application, this improved bound shows that in polynomial time, for the problem of Tensor PCA, increasing runtime, you can push down the signal-to-noise ratio by an arbitrary constant factor. So this is actually smooth. Like for example, if you know that right now you have an algorithm to solve this at some polynomial time, at some lambda 1, and you want to push down lambda to lambda 1 over 2 by doubling the runtime, you can actually achieve this. And our algorithm, our result also has some comparison to the quantum speedup. Previously, the quantum speedup is actually only saving a factor of 1/4 in the exponent. But now we are actually saying that for any fixed signal to noise ratio, we give you a super polynomial time saving in classical time. Not that you need to run the quantum algorithm. And our result is also interesting coming from random matrix theory again. If we compare our bound to the classical NCK inequality and the improved bound obtained by Bandera and co-authors last year. In this case, we are really saying, usually we expect matrix Bernstein or NCK to be lossy in the square root log matrix dimension factor. And we are confirming that, okay, indeed, it's two roots here. Like the square root log matrix dimension is needed. Some factor is needed. But as opposed to the result by Bandera et al., we can show that we are observing that for larger L, their bound is in fact too good to be true. Notice that they entirely remove the square root L log n here, but what we are getting is just removing the root log n, but keeping the square root L factor. So this is interesting as in it's sandwiched between NCK and when you expect NCK to be lossy, you expect the root log matrix dimension to be completely gone. So we are saying that neither of them is true. We are in the in-between case. So this result might not be that obvious or immediately guess if you just want to use like black box matrix concentration bounds, because you have predicted either of these two bounds.
So in the middle lower bound for the matrix Bernstein CK is no previously.
The lower bound?
Yes. I think
The upper bound.
explains in the middle one, like
we know that it's needed for some matrices. For example, you have diagonal matrices. You need the square root log dimension factor. But we suspect it can be lossy in other settings.
and then the upper right result can't apply.
Can you apply to?
The upper right result is too good. Like that mean does that mean
That means the bound is not true for larger L. For this matrix. It's like they are inherently bounded by the small L set. So yeah, I'm gonna quickly sketch the technical ingredients for our result, but don't worry if you get lost. Like, it's a warning sign. It's very combinatorial, but I hope you might like it. Like, this is what I think about previously. And to show you how to improve from the previous bound, we are actually just going to give you a reproof of those bounds with the polylog factors, but with our own twist. And then hopefully, like this is we'll see. So we are going to back to the start, and for simplicity, let's just look at Rademacher random tensor for now, and hope to recover the bound we get from NCK. So this can be proven by many of your favorite matrix concentration bounds. But we are going to do so by trace method, so that we can try to upgrade it and tighten it later on. So for the remaining of the talk, let's consider R equals to 4, first order tensor, and then L to be some gigantic constant. Not that you're going to actually run this algorithm in real life. And here's a generic approach for using trace mode method to bound the special norm of a matrix. It boils down to the following claim. For any symmetric matrix of dimension n, we can take it, we can bound a large power of the special norm of this matrix by bounding the trace of the matrix raised to a corresponding high power. And in fact, this is sandwiched up to a factor from over n. And here's the proof. The trace raised of a matrix raised to the power 2q is equivalent it can also be rewritten as the sum of the eigenvalues of this matrix. And now this is a PSD matrix and with eigenvalue given by lambda I raised to the power 2q. And you can easily lower bound it by 2q's power of the largest magnitude. So for random matrices, this is a generic approach to control the aesthetic spectral norm by understanding the aesthetic trace raised to high power. And here we are usually interested in Q to be logarithmic matrix dimension, so that we can get some concentration from Markov. So now this is a self-contained combinatorial question. For these specific matrix you have, how do you bound the aesthetic trace of the matrix raised to power 2q? And this is like a direct counting argument of length 2q walks. And for us, we really think of this as like, because this is a walk of length 2q, we're just going to bound the contribution from each step of the walk. And this is the main ingredient, really. And in the case of Kikuchi matrix of level L, let's look at what the walk looks like, just to get some intuition, if you want to play with it in some later on. So now the matrix indices is indexed by a subset of size L in N. So the walk roughly looks like the following. At each step of the walk, we're going to use some hyperedge or random variable, where each time we have R over too many active vertices. We pick R over too many, and then we kick them out, we swap them new ones, and then we keep doing this. This is a walk. And then as we said, the Kikuchi graph has degree D here for each vertex set. So each edge has choice D. So using the naive bound of each vertex has degree D, we are going to also observe that if you have in the walk, if you are going to use an edge that already appeared before in the walk. This is an encoding argument. This can be efficiently encoded at a cost of length of the walk. And yeah, so here's one setting. Like, imagine we are walking and then we're starting from vertex at S1 and then we take 3 steps and then now we're at S4. We want to decide which hyperedge we are going to use for the next step, with the promise that the hyperedge has been used before. So naively, this can be done by just specifying where I used this edge before. So this is a cost of 2q, the length of the walk. So, and here's another assumption we are using is that we are working with random variable of mean 0. So we can actually only focus on walks that use every hyperedge at least twice, or exactly twice even. Let me be precise. For any fixed walk, we can observe that this is giving a product of random variables on hyperedges. And then because they are IID random variables, I can write it as product of the expectations instead. And then if you have some hyperedge or random variable that appears only once, let's say, because you are looking at mean 0 random variable, this term is just going to be 0, it vanish. So we also can work with the assumption that every walk that we are counting use every hyperedge at least twice. So this is in fact sufficient to recover the NCK bound of square root D square root L log N as the following. We are going to observe that, okay, each step, if you are using a hybrid edge appearing for the first time, you get a factor D. But if you are using a hybrid edge the second time or the last time, you're going to get a factor 2Q. So this is our accounting. This, you can equivalently view it as each time we use a hybrid edge the first time, you get root D, root 2Q, and then the last time is root D, root 2Q. We are going to ignore middle edges for now. The edges that appear more than twice. They are negligible in our case. And this is fairly sufficient for now to recover the NCK bound because we have shown that each walk you have into the L many stars. And then for each step, you have contribution at most square root D times 2Q. So this is sufficient to get a bound of square root D 2Q raised to 2Q's power. And in the end, whatever inside the 2Q's power is the special norm bound you can hope for. I have to give that up. So let me skip through these. So I think we are really just observing here that using trace method, you can recover the lossy bound from NCK, and it also pinpoints to us that if you want to improve the dependence of factor 2Q, or you are trying to improve the combinatorial cost for an edge appearing for the last time. So the Polynomial factor entirely comes from this counting factor in this encoding. So here's just one takeaway from the message so far. It's a trace mode method allows, it's more complicated as opposed to just applying black box matrix concentration. It allows you to intuitively see what could be lossy in the NCK stuff. It's likely hard to see this from NCK, black box, if you want to open up the proof for NCK. Yeah. So in our case, we can show that the last cost can be improved from factor 2Q, which is Q is L log N to be L. And this is enough for us to get a bound of square root DL, which removes the root log N factor. And let me skip through these. This is but I want to say what's interesting is that our technique also allows us to see a lower bound and to really show that the square root L factor that is missing by the previous work of Bandera et al. Is necessary if you look at larger L. And again, this is done by a combinatorial counting argument. So let me quickly wrap up. Let's end by revisiting why we look at this question in the beginning. So we answered the question posed by Bandera and co-authors for larger L, what happens to this Kikuchi matrix? And this is some result that is not immediate with current understanding of free probability. And in fact, we show that the bound predicted by free probability is off in the larger L region for this matrix. And our work also really opens up this next question. Can we get this similar phenomena for CSP refutation? And once you can get a tight bound for the CSP refutation, this will basically answer the hypergraph move bound question. So I think this is an immediate next step. If anyone is interested. And yeah, thank you.
Questions? So I have a question actually. So I've been trying to follow the algorithm. It seems like the algorithms are very simple in some sense, right? But I'm curious how, if you think of more, instead of that, just think of like even stupider algorithms, which are just some kind of local search, like gradient descent over some model or some other kind of like local search. Do you know if do they perform at the same thresholds, or do you know how, either theoretically or empirically?
I think there is some free energy barriers that prevents you from getting all the way in polynomial. First of all, I don't know how to analyze local method, like power iteration for this large polynomial runtime, large exponential runtime. Okay. And then I think in polynomial runtime there is some free energy barrier.
Okay, so the way I would think of it for larger runtime is I'd look at some lifted model with like just do gradient descent. I wouldn't run my local search for or my power method for longer. I'll use a lifted larger model. So that each iteration takes longer time.
Yeah, I'm not sure about that. I haven't looked into those. Yeah, but we can.
Are there any formal connections between this and problems like planted clique or things like that? They feel similar. You know, you have this thing. Is it just random, or is it random with this extra thing? And so you can, if you can find, you need to be able to get out those correlations by taking a large set of vertices and looking at neighbors in common. And that takes into the L time for L being log n. I don't know. Is there?
Yes. Definitely. Like we get into this question before after we studied planted clique, and yeah, it seems like you are asking how to get this precise trade-off in signal noise ratio versus a runtime.
Or I don't know, or maybe are there like any reductions back and forth about, that could talk about if you could do better than this for one problem, you could do better than that for the other.
Yeah, it could be. I'm not precisely sure about the Tensor PCA question, but there are other problems in which case you can show using some variant of planted clique hardness. But I think there's one caveat with starting with planted clique is just that the best you can hope for is quasi-polynomial-time hardness. But here for this question, you can actually hope for some exponential time. So, you can get some quasi-polynomial-time hardness.
Additional questions?
So you mentioned that the probability bound for large L doesn't work. But would you hope it's like it can improve? Like what's the reason that it doesn't work? Does it provide a back bound for that, or it's kind of hard to define?
Why their technique doesn't work?
So what?
Why the previous technique doesn't work?
No, why the probability bound doesn't work for large L?
This one? This one. Their result doesn't work because this is not the right bound tool. The bound is off.
Yeah, so can you expect maybe a better bound if you use some probability stuff?
So in fact we can show that the outbound is tied up to constant.
Oh, I see.
So, yeah.
Okay, let's thank Jeff again.